Let's take a look at an example of a confidence interval for one proportion. So in this problem, they tell me that the results have a 48% success rate out of 331 Americans. And in this problem, we are looking at the proportion of people who decide to not go to college because they cannot afford it. And part A says calculate a 90% confidence interval for the proportion of Americans who decide to not go to college because they cannot afford it, and interpret the interval in context. Okay, let's write down some key information there and let's check out the formula and how this thing works. So they're giving me the confidence level, 90%, and the critical value linked to 90% is 1.645. And it's giving me a sample success rate, p hat, of 48%, which means our failure rate, complement, is going to be 1 minus, or 52%. It also tells us that we are looking at a sample of 331 Americans. Let's look at our confidence interval. So the formula for a confidence interval for P, starting out with what a confidence interval represents in general, is you have some sort of best point estimate center, some critical value, and a standard error. And when you multiply the critical value by the standard error, that's called the margin of error. So this is really center plus or minus the margin of error. In the case of proportions, this formula is p hat, our center is p hat, plus or minus z star, square root, and the formula for our standard error is p hat q hat over n. So everything after the plus or minus there, that's our margin of error. I'm plugging in my sample success rate of 48%. I'm plugging in my critical value of 1.645. My p hat, q hat, and number of samples, n. Well, I can type this entire thing into my calculator once with the plus and once with the minus. I'm going to calculate this margin of error because I'm curious how much our estimates here vary. So currently 48% of Americans are estimated to not go to college because they can't afford it. Let's see how much that varies. So I've got 1.645 times the square root of 0.48 times 0.52 divided by 331. And I want all of those things underneath the square root. So on some calculators, you need to have parentheses. On other calculators, you can actually see that the square root is covering them. When I do this, I get a margin of error of 0.0451 or so. And if I round properly, 1/7, so I'm actually going to make that a 2. I'm going to do this once with a minus and once with a plus. So if I take 0.48 and subtract 0.0452, that is giving me a low of 43.48%. Changing that minus to a plus sign gives me a high value of the interval of 52.52%. And if I'm interpreting these results, I would say that we are 90% confident that the proportion or percentage of Americans who do not go to college because of money is between 43 0.48% to 52.52%. So pretty close to half, maybe less than half, maybe more than half, but I'm 90% confident that the actual success rate is somewhere between those two numbers. And I'm going to pause this video for just a second, and I'm going to pull up GeoGebra, and I'm going to show you a way to double check your results using GeoGebra. Okay, I'm in geogebra.org/classic, and when I pull that up, it gives me this menu to the side. I'm choosing the option for probability. Inside of probability, I can go up to the top where it says statistics. So to double check my work, if I'm interested in doing so, GeoGebra, I'm choosing probability, and then I'm going to choose the option that says statistics. When I choose this drop-down menu, there are a bunch of things that say test. These refer to hypothesis test. And there are a bunch of things that mention an estimate. Estimate is how we do an interval. That's a confidence interval. I'm looking at a confidence interval, so I want an estimate. I'm looking at a proportion. So these are all talking about means of a proportion, the difference of proportions. So if I have one proportion, I'm using this first one. If I have multiples, I'm using that second one. So z estimate of a proportion. So the z estimate of a prop. And for the confidence level, 90%, 0.90. And it didn't give me the number of successes, and it's asking me for the number of successes. So in GeoGebra, I can just type 331 trials, and there was a 48% success rate. So approximately 159 successes. I could type in 159 if I wanted to. For the number of trials, I have 331. This gave me an interval of 0.48 plus or minus this 0.0452. So my interval setup looks the same. And a quick glance at the low value and the high value show me that those match up as well. So GeoGebra is a really nice way for me to double check my work. There is a second part to this problem. Suppose we wanted the margin of error to be about 1.5%, still at this 90% confidence level. How large of a survey would you recommend? So currently I have an error of close to 4.5%, and that was for 331 samples. If I want less error, I'm going to need more samples. So what I've got going on I'm going to use our p hat of 0.48 as an ongoing estimate here. And if there is no estimate given, 50% is a good amount to use as a rough estimate just to get started. And a critical value of 1.645. And my margin of error was everything after the plus or minus. So they want that value to be 0.015, 1.5%. Let's blow up that overhead to make that a little bit easier to see. And let's write out our margin of error formula. The margin of error is our critical value, square root p hat q hat over n. I'd be careful with my language. If it said standard error, it would just be the square root. If it says margin of error, it includes that critical value z star. Now my margin of error is 0.015. Critical value, or my z star, is 1.645. Square root, my p hat, my q hat. And I'm trying to figure out how many samples I need, n. So I'm going to do some arithmetic here to solve for the n. First thing I'm going to do is I'm going to divide this over to isolate or get that square root by itself. So when I divide that over, that 1.645 ends up in that denominator. To get rid of this square root, I need to square the fraction. So I'm squaring both sides. Squaring this side cancels that, they're inverses. And squaring this side will square both the top and the bottom. I'm squaring the entire fraction. So I've got rid of the square root in favor of squares on the other side. I now have a fraction equaling a fraction, and one strategy for solving a problem with a fraction equaling a fraction is cross multiplication. So I'm going to take these denominators and multiply them across. So the n is going to get paired up with that 0.015 squared. So 0.015 squared times n. I almost have n by itself now. And this 1.645 squared is paired up with a 48 and 52. To get rid of this multiplication, as a final step, I divide, and this gives me 1.645 squared, 0.48, 0.52, and I'm undoing this multiplication, so I'm bringing this under here, 0.015 squared. I'll type this into my calculator and I will round it up because I want to make sure I have at least that many samples, if not more. And I'll round up to the nearest person. So I've got 1.645 squared times 0.48 times 0.52 divided by 0.015 squared. And when I do so, I get 3001.88. Even if this was 3001.11, I would still round this up to the next highest number. In that case, 3002 individuals. I can still use GeoGebra to double check this number, because if I change this 3002 times that same success rate, 48, to get some number of successes, if I change this to 3002, I should now see for this interval, I'm adding and subtracting this new margin of error of 0.015. That's my desired margin of error. I'm going to type these results inside of MyOpenMath. It says type in the lower bound, and it wants it to 4 decimals. So it wants it in the decimal form. My interval was 43.48% on the low. And on the high, I have 0.5252. And I just clicked that, but I'm reading these. We can be 90% confident that our confidence interval contains the sample proportion. So my conclusion should be about a population. I plug in sample information, but it spits out information about population. So that's not what we're looking for. We can be 90% confident that the proportion of Americans who choose to not go to college because they cannot afford it is contained within our confidence interval. Oh, so I actually did randomly click the right answer there. Great. 90% of Americans choose not to go to college because they can't afford it. 90% isn't the value we're confident about. We're really confident about this interval, this 43 to 52. And for the number of people that we had to get, we got 3002. So this is what I have for my answers here for this question inside of MyOpenMath. And when I check, I get green, green, green all the way down. Looks great. As always, I am around if you have questions, but I hope this helps you out a bit for getting used to setting up these confidence intervals and also solving problems involving given margin of errors.